so this question links the normal distribution with some hypothesis tests and all the terms you need to know surrounding hypothesis testing. So we've got these weights and bars of soap. The standard deviation is 3 grams. It says the weight is 120, so that's the expected mean. Gazelle believes the mean is greater than, so her belief is that the mean is greater than that, and she takes a sample of 10, and she tests at the 5% level of significance. So the probability of type 1 error is the same as the significance level, so that's 0.05 or 5%. That's just a straightforward knowing what that term means. Right, so now we know the true weight is 122, and we've got to show the power of this test. So power is the probability we reject H0 correctly. Okay. What we have is we would be testing that the mean is 120, and the alternative is that the mean is greater than 120. So if H0 is true, then the mean weights come from a normally distributed with a mean of 120 and a variance of 3 squared over 10, because we're taking sample means, so we take the variance and we divide by the sample size. Right, then what you can do in your calculator is work out what the critical region is going to be. So we can work out what this is such that we get it's a one-tailed test, so we want 0.05. And so if you do do an inverse normal distribution in your calculator with the mean 120 and the standard deviation of 3 over root 10, you can find out that the critical region is that the mean weight has to be greater than 121.56. So if you don't have a calculator capable of doing that, you can do that using the standardizing you've learnt from maths. So what do we want to know? Well, so our power is the probability that we are in the critical region. So our mean weight comes out to be greater than 121.56, given that the mean is actually 122. So that's 0.6786 and some more numbers if you work that probability out in your calculator now. So we put in the mean, we put in the same standard deviation, and we put in our x value as 121.56. You should show more sig fig because it was a show that, so we want to show that rounds to 0.68. Okay, so then Alex is going to carry out the same test, but he's now using a 1% level of significance. So we've got to compare the power of his test with the power of Gazelle's test. So remember, power is the probability you correctly reject H0. Okay? So what's going to happen is, because Alex is less likely to reject H0 because he's only got a 1% level of significance, the power of Alex's test will be lower. Just checking. So the power of Alex's test will be smaller than Gazelle's, as he is less likely to reject H0. Okay. You could also explain that in different ways. You could say the probability of a type 2 error has increased because the power is 1 minus probability of type 2 error, but I find that's the simplest way to think about it. Okay, so now we've got somebody else, and now Joseph is going to increase the sample size and carry out the test at the 5% level of significance. So again, we're assuming the same, the mean rate is 122, and this gets a little bit more complicated. We want the smallest sample size that will produce a power of 0.9. Okay, so first of all, we're going to need to know what our new critical region is. So now our means are going to come from a normal distribution under H0. So if H0 is true, with mean 120, but the variance is 3 squared over n. We don't know what n is. N is what we're trying to find. That means we're going to have to do a bit of standardizing. So if I call my critical region x var is greater than c, so I'm trying to find c. So we're going to have to do a bit of standardizing from your maths where you learn the standardizing formula. So that's our value, which is going to be c, take away the mean, divided by the standard deviation, and we're now going to have to look up using z. So what we want to know is if we can have the 5% level of significance, there would be our c value, but we're going to do this using z tables, so or using your calculator. So remember that z comes from a normal distribution with a mean of 0 and a variance of 1. So we can work out that the z value corresponding to 0.05 at the top end of the table, so this is right end if you're using your calculator, is 1.6449. So using our standardizing formula, that must be equal to 1.6449, and I can rearrange that to find out that my critical value is going to be 1.6449 times 3 over root n plus 120, which is still quite a long looking formula. Now, our power, which we want to be 0.9 or better, is the probability we correctly reject H0. So that's the probability of being in the critical region, given that the mean is 122. And we're now going to do all this standardizing again, but with our new mean. So what do we want now? Well, now we want, when the mean is 122, we want to have a probability of 0.9 that we get a value greater than c. So again, we're going to have to turn that into a z. So it has a mean of 0, and I want to know what the z value corresponds to 0.9 on the right hand side. So all of that means that we want c, so our value minus our mean divided by our standard deviation equal to, and if you look this one up, you get negative 1.2816. Okay. Right, now it's just a case of substituting in what we know c to be and doing some rearranging to find n. So you just plug in your value for c there. It's important to note here that because our z value is below the mean, it is going to be a negative value, and that way you can make sure you're talking about the right thing. If you then rearrange and solve all that, you should get root n is 0.38975, and that gets you n is 19.269. Now, obviously n has to be an integer, so now we've got to think about which way it is. Now, so n is either going to be 19 or 20. Now, 20 is larger than 19, and what we're doing is we're dividing by n. So if we divide by 20, that's going to give us a smaller critical value, yeah, than 19. Okay? Then c is going to be a smaller value. So that means on our diagram, it would be more to the left, which means the power, this area, increases, oops, I'm sorry, that's what I hit there, which means that area increases. So if the area increases, it will go above 0.9, whereas if m was 20, then RC would move to the right, and then the area would end up being below 0.9. If you find that a bit confusing to think about, what you could do is just type it into your calculator, so find out what the power is, and if n is 19, you get a power of 0.895, and if n equals 20, you get a power of 0.909, so it's obvious that n equals 20. Or you can do that whole thing with inequalities, just be careful to make sure if you divide by -1 that you change the sign around. So that's the hardest bit of this question. So the last bit is, should we use Giselle's or Joseph's test? Okay, so we want to compare their two tests. And when we're comparing hypothesis tests, the things we want to compare are the size and the power. Okay? So size being the probability of a type 1 error, and that's the same as the significance level. So if we have a look back, they both use the 5% level of significance. Power, well, we've shown Giselle's was 0.68, and Joseph's, you don't actually have to work it out, is going to be greater than 0.9. Okay, so size is the probability that we are going to make a mistake and reject H0 when we shouldn't have. Now they're both the same, okay, so we want a low size, so that's okay. Now power is the probability we correctly reject H0. So we want a large power, so we want this one to be small, we want this one to be large. These two are the same, but here Joseph's has the higher power, so you would say that both tests have the same size, but Joseph's has the higher power, so we would use Joseph's test.